Hi, my name is Lauren James, and for my Satellite and Radar case study project, I'll be analyzing Hurricane Helene's radar data to understand its structure, the intensity, and some of the unique features of this storm. Base reflectivity measures the precipitation intensity, and it really highlights the eye wall and the rain bands. As you see on the screen, we have the hurricane here a few hours before it made landfall. This is around 6 p.m. Looking at the Tampa radar. You can clearly see the eye and the rain bands around the storm here. If we look closely, I'm gonna use the inspector tool so we can see the DBZ values around the eye wall. So as you can see here, there are DBZ values exceeding 50 decimals. So this is tightly wrapping around the eye wall. So that basically is signifying that there is a strong, intense area of thunderstorms around the hurricane's eye. So there's some intense updrafts, heavy rainfall, and that's just signifying that this is one of the most damaging parts of the storm. Notice that the rain bands are more developed on the northern side. As you see, the storm is kind of asymmetrical. The northern rain bands are stronger. If I switch to Tallahassee, switching to the Tallahassee radar, you can see that the rain bands from Helene are stretching deeply inland towards Georgia, the Carolinas, and Appalachia. So there's a lot of persistent heavy rainfall that's going on with this storm. And even further north, if I were to look at Atlanta radar, there's a lot of heavy rainfall across the states north of the storm. So this definitely contributed to some of the historic flash flooding that we saw after landfall, and some areas received over 15 inches of rain. This storm resulted in flash flood emergency warnings all across the southeast United States. We see Virginia, Tennessee, West Virginia, Kentucky, Ohio, North Carolina. But this is likely developed more on the northern side due to upper level wind shear. So now that we've seen the storm structure, let's explore the powerful winds using the base velocity. So I'm just going to go a little forward in time so we can see the storm moving closer to land. And I'll have a dual screen so we can also look at the velocity as well. Okay, look at Tampa. So looking at the base velocity, we can tell that there is a symmetric velocity pattern around the eye. And there's also some strong inbound and outbound winds. When we get closer to the time of landfall, and I'll switch over to the Tallahassee radar, that's more north, closer to the Big Bend. Okay, so switching to the Tallahassee radar as that's closest to Perry, Florida, where the hurricane made landfall, we can see that with the inspector tool, the winds are very high. The base velocity here is basically showing the wind moving towards and away from the radar. So this red is moving away from the radar, and this green is moving towards the radar in Tallahassee. And if you look closely, we can see that there are very high, strong winds. It's exceeding 140 miles per hour, which is categorizing this as a Category 4 hurricane. Landfall was around 11 p.m., so I'm going to move a little bit forward to after landfall. I want to call out here, after landfall, we see a decrease in velocities. This is due to the surface friction and it's weakening Helene's core winds. And we can clearly see here that the winds are weakening after making landfall. We're not seeing those super high winds that are around 140 miles per hour anymore. So as we see, once again, this is 10:30 before the landfall, and the winds are still very high, categorizing a Category 4 hurricane. And if we move forward into early morning, the next day, we're seeing that these values are decreasing. Just wanted to show it again while playing it. These winds are moving away from the radar, and these winds are moving towards the radar. I'll go a little bit further in time just so we can continue to see how the winds weaken due to the surface friction as the storm moves further inland. Now let's take some time to explore some of the biological phenomena that happen inside of Helene. And we can do this looking at the correlation coefficient. So the correlation coefficient measures how similar the radar targets are. So like if it's high, that means raindrops, and low values could indicate debris or biological matter. If you look inside of Helene's calm eye here, we're seeing low CC values. So that's indicating that there is likely birds, like thousands of birds in the eye, trapped in the eye. And I'll go forward a little bit in time. We can see. And as it's over Perry, Florida, we're seeing those low correlation coefficient values. So yeah, this is indicating that thousands of birds were trapped in the eye during the storm as it was passing. And also, if we look at some of the outer bands, we may see some potential tornado debris signatures signified by the low correlation coefficient values. During Hurricane Helene's passage, several tornadoes were confirmed across the southern eastern part of the United States. As you see here, there are tornado warnings out in Florida, Georgia, and South Carolina. You can see specifically here north of Augusta and even further north. Even before the hurricane made landfall, there were tornado warnings in effect in Florida, as we see here. Looking at the correlation coefficient, we may be seeing some tornado debris with some of the low values that we are seeing here outside of the zone of the tornado warnings in Florida before the hurricane made landfall. To detect more detailed internal rotations, let's now view the storm relative velocity. The storm relative velocity removes the storm's forward motion and it really puts a focus on the embedded rotation. At 11:30 p.m. on September 26th, the Tallahassee radar was capturing significant storm relative velocity data as the hurricane was making landfall in the Big Bend region. We can see that there are strong winds. We can see here in the northeastern quadrant, there are intense inbound winds and they're moving towards the radar site. So this is suggesting that there's a strong eye wall and potential for severe weather conditions. Also, on the west side of the storm, we're seeing the outbound winds, and it's indicating a rotation of the hurricane's circulation. We can also see some tight velocity couplets, which is indicative of wind shear and potential tornado development within the storm's outer rain bands. As Hurricane Helene approached the Florida coast, the storm relative velocity data from the Tallahassee radar at 0.5 degree tilt revealed some tight rotations within the eye, also known as mesovortices. These features are indicative of intense internal dynamics within the hurricane's core. Immediately after landfall, there's still the continued presence of metavortices as the eye is moving inland. I'm looking closely here, trying to observe any changes in the storm relative velocity pattern because that can indicate some structural evolution with the eye wall. But since the storm relative velocity image still shows some metavortices, this is suggesting that the storm is still sustaining its internal rotation despite the interaction with the land. This is really highlighting the storm's intensity and structural integrity. So now I'm going to move forward. So about an hour after it made landfall, the data is starting to show signs of an eye wall replacement cycle. There's a formation of a secondary eye wall, and this transition is pretty critical to understand so that we can understand the storm's potential for re-intensifying or any structural changes. About 30 minutes later, at 1 a.m., we can see that the evolution of the outer eye wall is becoming more dominant and the inner rotation eye wall is starting to weaken while the outer eye wall is starting to circulate. Throughout this video, I'm referencing the Tallahassee radar quite a bit here, but it was just in the perfect position, especially at this time. It was approximately 90 miles south from the storm center, and it was just positioned perfectly to capture the landfall. So this proximity is allowing for detailed observations about the storm structure and dynamics. There's critical information here about the storm's intensity and potential impacts, including the likelihood of tornadoes and the severity of wind gusts. So this data is very valuable for issuing timely warnings for public safety during the landfalling hurricane. Now I just want to summarize everything that we just discovered through the radar. We examined Helene's eye wall and the rain bands through base reflectivity. We looked at the strong wind fields via base velocity and storm relative velocity. And we identified a unique biological signature using the correlation coefficient. Hurricane Helene's rapid intensification and widespread flooding across multiple states across this region really highlights the crucial role of radar, not only for coastal impacts, but also for communities that are far from the shoreline. Understanding storms like Helene really helps meteorologists, scientists, and the public better anticipate and respond to future severe weather threats. So I appreciate you for watching, and thank you.